welcome back to the lecture series on this GPU architectures and programming. So, we will start with one very relevant topic right here, which is like how this paradigm of GPU programming, or better to say in general SIMD style programming, how does that really help in accelerating ML workloads. And to be more specific, we will focus on how this kind of architectures help to accelerate the execution of several, both neural networks training as well as inferencing process, because as we all know, these are the most relevant workloads, at least in the ML CS community and also CS community in general, and also in it's finding lot of applications in several cross disciplinary areas. And in terms of system execution, we can always say that this is the basic reason why this kind of neural network based systems are finding popularity is that there is a lot of data available nowadays, point 1, and point 2 is of course, we have got this kind of large scale systems where I have the facility of GPUs to accelerate parallel programs run times by several orders of magnitude, we would say, and that really helps in realizing this kind of large scale deep neural networks, and they provide us significant and more and better to say usable accuracy in many application domains. So, with that background, we like to quote the famous researcher Tom Mitchell here, where he says that a computer program is said to learn from experience E with respect to some class of task T and performance measure P if the performance it provides at tasks in T as its, and the performance measure of course is P, it improves with the experience. So, the more experience you provide it with, it is learning better how to execute this class of tasks with respect to a performance measure that is defined by P, right. So, we can say that it is learning from experience provided it excels in future executions of such task instances for maybe newer instances of data. I will just like to notify one very important thing, that the preparation of this set of slides have been significantly helped by my wonderful teaching assistant Anirban Ghosh, who really has done a great job in helping me prepare this slide sets. Of course, the others were also there, but in this slides he has got a huge contribution. Fine. So, just the way we will approach it is that we will just give a brief overview of the basic computation that is performed while training a neural network for some task. So, I will just put in a note here that this is not going to be a ML kind of lecture where we go into the nitty-gritties of what is learning, how is it done and all that, but rather we will just take a specific workload which is neural network training and inferencing process. We will just identify what are the computational parts of that, and then we will map those computational parts to GPU architectures and see how they can be accelerated. That would be our approach here, to be very clear. So, doing a quick brush up of the learning techniques, as we all know that, so these learning paradigms can be divided roughly into 3 aspects, like you have supervised learning, unsupervised learning, and also there is this other paradigm of reinforcement based learning. Strictly speaking, if we just consider supervised and unsupervised learning, in the first case we consider a set of labeled data that is already provided. It's labeled like you have a data set and you have tags which actually say which are the positive as well as the negative, or some other kind of classification tags are also there which give you some information about the data set. In the other case, which is unsupervised, there is no such, better to say, supervision available, that is that for the data you do not have any such tags that are available. So, all ML techniques which work on the first kind of data are kind of classified under supervised learning paradigm, whereas the other case we call it as unsupervised learning. So, in general, when we are talking about a machine learning system, so it has got a set of tasks T, where you are trying to learn rules or functions based on such examples, right. So, the examples can be characterized by a vector of real numbers or Boolean variables depending on what kind of task we are talking about. Each example may have a target label, like we discussed supervised learning. In that case there is a target label. In case it does not have any kind of such labeling, we call it an unsupervised learning system. Examples are not available explicitly, and some agent environment interaction must be envisaged to extract meaningful examples, which is the case for reinforcement learning, which is gaining a lot of traction nowadays. So, like we say here that the examples are not readily available, but you set up an agent environment interaction. So, you kind of model the environment, or you kind of put in a learning agent which is trying different possible moves in the environment and finding out how good is that move based on some runtime evaluation, and that data is kind of used to figure out, well, what is a meaningful example, and then make good use of that example to learn a classifier or a similar kind of system. So, and then we have this issue of experience. So, of course, more experience means you have a bigger data set with rich examples. Now, of course, this is something which will be well known in the ML community, that of course, you can have a big data set, but that does not mean that it is rich. There has to be enough information about the state space that you want to learn. So, the amount of data in the data set may not be that important as like the richness of the data set in terms of information that can be mined from the data set about the characteristics of the state space. Then, well, what is really performance? Performance refers to some metric for accessing the quality of the function that has been learned. So, well, at the end of doing all the training and everything based on the data that is provided, you learn a function, but you have to calculate whether that function is good enough as for some deployment scenario or not. So, you need a measure. Usually we call it a cost function, which evaluates the performance of whatever function or rule you have learned, right. So, in our lecture we will discuss only supervised learning kind of problems, and this kind of problems. So, that means we are assuming there is a training data set with proper labeling that is available, and that will be used to learn proper rules or functions. And for this kind of problems, the primary classification that is done is like well, you can have a classification task or you can have a regression task. These are the two kind of systems that you can really learn. So, when you learn a classifier, that means given a new data input, you can infer the class of the data. So, basically you can kind of classify all the inputs to certain categories, and you are trying to for a new input you are trying to find, well, which category it best fits in. So, that is called typically a classification task. On the other case where we have a regression class. So, regression would mean that you have this input data and you are trying to find out a fitness function, like what function would fit that data pattern nicely, so that then again I would say you are learning a continuous function, so that given any new data point, this continuous function will give you a possible value for as an output, taking the new data point as an input. So, in general, when we are speaking of supervised learning tasks, we always have a generic workflow like this. That means, you have a training data set with labeled data, you have this supervised learning algorithm which will work on this data, and at the end of the day what it will come up with is a predictive model. That model can either be a classifier or it can be a regression model. Now, well, how do I test the goodness of this model? I have trained it using the training data. I have figured out using some algorithm which ran on the training data that this is the model I am getting. Now, to test the fitness of this model, I give you some other data as input called the test data set, and using this test data, I check with what is the inference that is done by the model, what is the classification of the new test data, or what is the regression value that this predictive model computes. Well, but this is test data, that means for the input values I also have the suitable output candidates available to me, right. So, based on whatever the model is predicting and whatever is the real output value that was supposed to be in the test data, I calculate some error, and that is measured by the loss function. So, I have this concept of loss function. I mean, why do I have this function? Well, there is an error, right. I have calculated something and using my predictor and there is something that the test data really tells that this should have been the real output. So, there is a difference, right. How do I really characterize this difference? Because we are speaking of data in a high dimensional space, it is not like a single tuple, the value is 1 which is predicted, whereas the actual value must be 1.1. It is not really like that in general. We are talking about high dimensional data. Borrowing from linear algebra, we are supposed to bring in a possible fitness function which characterizes this distance metric of in the high dimensional space, that well, I am predicting this point in an n dimensional space, whereas the actual output is this point in that same n dimensional space. So, I need a suitable distance metric which I characterize by choosing a loss function, and then using this loss function I generate something called an error signal, right, which I can typically use to refine this predictive model, right, and that is how the loop will go on. And finally, if I see that whether I am happy with the accuracy that I am getting. So, if I see that well the accuracy is not good enough, then I say that well, this system is not learning enough from the training data, I may read some more data, or I may need to change the supervised learning algorithm itself, or the other alternative can be that I need to change the parameters of the algorithm, right. So, this is the generic flow that I have for any supervised learning system. So, you build the model, you tune, you evaluate the quality of the model, you accordingly tune parameters of the model to figure out whether you are getting a better model or not. And once this step is complete, so as you can see that this is an iterative step, you are building the model, you are checking the error that is generated, based on that you may be tuning parameters of the model here, but finally by after exploring all the options in the parameter space, you can report a maximum accuracy. If that is good enough, you are done. If that is not good enough, you change things here, or you may say that well, even changing here is not helping me, you increase the input data set by some way. So, even if by changing algorithms it is not really helping, that means this training data set is not really rich, you are not covering enough aspects, information theoretic aspects of the input state space of the model, fine. So, now if we just enlist things step by step, so any standard supervised learning algorithm would have the following characteristics. It will characterize the model to be learned by some parameter theta. It will define a loss function between the predicted output and the actual output. It will update this parameter theta, that is kind of parameter tuning, as long as the loss function's value is not minimized. So, of course, as you can see that the loss function's value depends on the model, right, that I have trained, and inside the model I have put in this unknown variable which I am calling a parameter of the model. So, typically what is the parameter? So, let us say I am defining a function f x for y. Instead of that I write well, let the function be f x theta of y. So, this is the normal mathematical function we are used to. X is the input, generate the output. Instead of that, all that we are saying is the output is y. This function is not only characterized by the input, there is a theta, right. Well, what can that mean? Let me just take an example here. So, let us say I am just trying to write a closed form expression to motivate the problem, do not think this will be the actual thing in general. So, let us say the function is 5x plus theta by 2. I am just writing one function here. All I am trying to say here is, so you can see that the value of the function for certain input x not only depends on the x itself, but also on what value of theta I am choosing. It can be 0 to say that it is absent, it is not really influencing the function 5x. It can have a value 0.1 to say that well, I am not biasing the output of 5x by much. It can have a value 1000, which can say that well, I am giving a big shift, I am giving a big positive shift in those cases when the value of x is, let us say, less than some value like 200. I am just trying to motivate, again I would say this is nothing this is not a strict mathematical characterization. I am just trying to say that if you draw this our favorite coordinate system, and then if theta is really not there, you have a line like this, a slope, right. If you put a small theta, you are just giving a small constant value to that slope, and then again if you have a big value already here, then initially well you are rising from here, but this there is already a significant value. But again this is a very naive example, I would say. In general, theta can be very having a very complex relationship, because x may be a high dimension in the high dimensional space and all that, right. So, all that we are doing is we are saying that wait, in that model there is lot of information I do not know, and that is what I am characterizing by the theta, and I am asking the learning algorithm to figure out what should be a good value of theta, so that the loss function, that is the error in my estimate, is getting minimized, right. So, the more the loss function is closer to the minima, the more closer is the predictor output to the actual output. So, in that case I would say that well, in that case I have chosen the theta in such a way that it approximates the actual functional relationship very nicely, right. So, essentially this is nothing but a kind of estimation of the parameter theta. So, we will start with regression here, like as we discussed that regression is nothing but learning a continuous function. So, you have a data set, a labeled data set, given inputs y, you have outputs x, right. So, you have this kind of values like that, and you are trying to figure out what kind of curve would approximate it nicely. As you can see, this is not going to be a good approximation, because there are several values which are lying at quite a distance, right. So, in general that is what I want to learn. I want to learn a function f which is parameterized by x as well as theta. I mean it takes as input x, it is parameterized by theta and it is going to output y, and I want this function to fit the test data as nicely as possible, right. So, I want to learn this function which can predict any new for any new x what is the output level y, and I want that to happen with reasonable accuracy, right. So, what we can do is let us say we make a linear approximation here. So, let f x be some w x plus b, and I want to parameter. So, essentially this w and b represents, it is like a form by which I am saying that the parameter theta influences x, right. So, in this case I am saying that let theta be such that it is essentially a pair w and b. The first item w is just scaling x, and the b is giving a constant DC shift, right. So, I have a function of this form, and I want to tune the slope and the intercept, so that I get a functional representation, a linear representation which fits these input values as nicely as possible. Now, of course, in general this input data can be high dimensional, like we have been saying, right. So, x can be a vector comprising x1, x2, x3 up to xn like that. So, then I am not even I am also not saying that w is a scalar, but rather w is also a row vector. So, that essentially we are speaking like this, that this is, so theta contains values w1, w2 like that up to wn, which gets multiplied with x1 and up to xn, and then I have the shift b, which is the value here, right. So, essentially in this case I am saying that we are trying to figure out a function which fits in a multidimensional space. So, this kind of linear binary classifiers are what we have been popularly knowing them in the literature as perceptron, right. So, consider a data set like this, xi, yi, these are the training data that are there. For given xi input, the output label should be yi. Now, we are saying that well, they are all values where the dimension d, right. So, that is why xi belongs to r to the power d, and in this case we are considering a binary classification. That means, the outputs are either 0 or 1. So, as you can see, we are making a jump here. This is our model for regression, which we have spoken about. So, in that case we are trying to approximate the data by a continuous function. The other problem, as we discussed earlier, is classification. Classification means, given some input, I want to see the membership of that value of the resulting output to a class, right. Now, in a simplest possible case, the class can be binary. So, in that case I will say that well, I have class 0 and class 1. So, for a given input, just see whether it goes maps to a 0 or a 1. So, that is why this is a simple linear binary classifier, or in other words we call it as perceptron. So, a simple perceptron here. So, we learn a function for this problem, where we are trying to figure out what is the suitable settings of theta, such that I have a nice I mean the most accurate possible binary classification. So, we are trying to figure out f theta x equal to y that can predict any unknown x j which is not in the data set with a label y j, which with reasonable accuracy, of course. In this case also we consider this f theta to be of this form, that given any x I am trying to figure out first what is this what is going to be the linear scaling here. That means, in this case we are saying that well, you have this set of weights w 1 to w d. I am considering that x is a vector of size d, and they are all getting multiplied by the x 1 to x d's, and so kind of I am trying to see what is theta here, right. And then also we have another parameter, that is b. But wait, there is something more here, right, g. Now, what is that? So, in this case what we are doing is, we are saying well, let us first apply our linear scaling idea which we discussed for the regression problem, right. So, essentially we have a linear function map which is taking the input vector x, generating a single value by multiplying it with a row vector w 1 to w d, and then adding a constant shift b, right. But does that solve our requirement? No. What is the requirement? The requirement is not to figure out a real value y, but rather to figure out a Boolean value y which is taking either a classification 0 or 1. So, what we do here is, whatever we get out of this calculation, we map it to something called an activation function, which will perform the final classification. So, it will have a thresholding nature, so that for up to some values it may map it to 0, up to some values beyond that it may map it to 1. It will have some kind of thresholding feature, which will be useful to get the initial computation of the linear function mapped to a corresponding 0 or 1 partition class. So, if we try to use this idea and design an algorithm for performing such classification task, one can be as follows. So, you have this kind of set of inputs x, and you have for them the actual outputs known for them, right, the yi's, and you are trying to estimate what should be these parameters w's and b's. So, what you do is, you run an algorithm through which what you are trying to see, you are trying to have some initial values for these w's, you use them to predict the y's, and then you figure out what is the difference between the actual y and the predictor y. So, that is your error. You multiply that with a constant eta called the learning rate, you multiply that with that positions x value. So, I mean we will come and see why we are designing this like this, that will come later on. Let us just try to assume that here you are scaling this error by these values and trying to figure out what can be an incrementally better estimate of w. So, this calculation gives you a modification in W, you add that modification here. So, this can be a positive or a negative quantity, you get a refined parameter W, which you will again push into the end this loop again. Let us understand all that we are doing. We are using a set of x, we are assuming a set of initial W's, we are using them to estimate a predicted value of y. Then we are calculating what is the difference between the predicted value and the original value, right. Again here we are making use of a Heaviside as a thresholding function like g, and then we are getting an error. That error we are multiplying by a constant as well as the current x value for that component, right. And then what we are doing is we are modifying the W. Let us try and understand again. So, this is a simplistic case, right. All we have done is we have removed the b here, assume it to be 0, we are just playing with W simplistically. We are using one threshold function called Heaviside, check what it is, it is a simple thresholding function, and using Heaviside we are thresholding it to get a predicted value of y. We calculate the error, multiply by learning rate, the value of the chosen x to get a possible shift in W and accordingly tune W. We keep on executing this loop as long as we are not really satisfied with the values that we are coming, that is what we will define as convergence later on. Now, we are just let us now try to give an example here that how really that looks like. Consider a 2-dimensional space, you have x's and y's and we are trying to learn a classifier, a linear binary classifier or a perceptron here. So, let us say these are your data points, and in an ideal system this is your classification line. So, these are the data points that should be in one class, these are the data points in blue that should be in the other class, right. If you start executing our algorithm that we just discussed, what may happen is you start with a test classifier like this. So, this is the line that you are getting by assuming some initial values of W's, right, because what does really the initial values of W give you? It gives you a line, right. Of course, here you also have a constant value b which is not 0, right. Now, as you keep on executing that algorithm, those values of W will keep on getting tuned, it will keep on changing, and what you expect is that with certain time you are going to get possibly a good approximation. Now, why is this a good approximation for this classifier that we hypothesize? Because as you can see that this rightly classifies the data points of one class which is marked in red from the data points in other class which are marked in blue, right. So, that is a good classifier then. As you can see they are not identical, but this serves the same purpose at least in this case. So, with this I will have reached convergence, because since this is also correctly classifying all the data points just like the original hypothesis classifier function. So, I do not have anything new to learn from this data set, right. So, I will have received convergence and I must have stopped here. Consider certain examples here. For example, suppose I am trying to learn a NAND relationship. So, what is NAND? So, this is the truth table of NAND here, right. Consider that you have inputs x1 and x2, right. So, you have an input x, a 2-dimensional vector, a 2D you have input x which is a row matrix or a column matrix of size 1 cross 2, and you are trying to just classify it to a binary classifier to a 0 or 1. So, that is like learning any 2 input Boolean function. In this case the choice is NAND. We have the truth table of NAND here, both zeros you get a 1, 0 1 you get a 1, 1 0 you get a 1, only when you have both 1s. So, that will give you an AND which is 1, and now you negate the AND to get 0 which is the NAND value, right. If you plot this here in your coordinate system, so the positive cases are the green points, right. So, and for all those cases you have so essentially we are just plotting here the x's and y's, x1s and x2s, right. So, in this direction you have x1, in this direction you have x2, and here we are just trying to see what are my positive cases. So, 0 0 is a positive case because the output classification is 1. I am just saying positive negative in sense of 1 and 0 and all that, and you have 1 0 and 0 1, 1 0 and 0 1 both also as positive cases, right. Now, for 1 1 that is a negative or 0 class classification which is marked in red. If you apply the previous algorithm here, you will learn this line, right. So, as you can see, the classifier does its job because it is classifying everything that is positive on one side, keeping the 1 value here on it with suitable tuning or redefinition. I can put it, I mean, like this. So, the classifier is doing its job. An interesting question in this case can be, what happens with XOR? First of all, let us understand that we are learning a linear classifier here. That means, we are considering that these points are linearly separable, right, but in general it may not be so. So, let us see why, I mean, this method may not be working so well with XOR. What is the truth table of XOR, by the way? Right. So, the next task is to figure out whether this is linearly separable or not. So, if you use the previous method, then you have 0 0. So, that is a 0 class classification, 1 0 and 0 1 as 1 class or positive classification, and this is again a 0 class or negative classification. As you can see, you cannot draw a line which will put the zeros on one side and ones on the other side. You cannot have such a relationship here. That is why the XOR relationship will not be linearly separable, and this algorithm where I am assuming that the function approximation is going to be a linear function is not going to work, right. So, we have to see how things can be managed at this point. With this, let us end this lecture and we will take it further from here in the next lecture. Thank you.